So looking now at hypothesis testing for a two-sample question in which the samples are independent. First of all, what do we mean by independent samples? We don't have that direct relationship between the first and the second sample like we had with matched pairs. Remember, with matched pairs, we had to know that in our first sample, the items directly correlated to a specific item in the second sample. So if I had Jim's value before some event, I would need Jim's values after an event. If I had Heather's values before, I needed to compare those to Heather's values after. Here it's not going to be the same. We don't have a direct relationship between the before and after events or between the two sets of data. So instead of just subtracting each value in column A from its related value in column B, that really wouldn't make a whole lot of sense since there's no relation between those two values. What we'll do now is to take all of the statistics we need for sample A and all the statistics we need for sample B and then compare them at that point. So we'll get the average from A and the average from B and then subtract those, not each individual data point because it really doesn't make sense with independent samples. But after that, really most of this is exactly the same. What we're trying to decide, is there a difference between sample A and sample B? Well, if there is no difference in our null hypotheses, then we would have that mu1 minus mu2 should be equal to 0. And then our alternate hypotheses will also depend on the language of the question. If it just wants to know if there's a difference, then we use not equal to, a two-sample test. If it asks if there's been a decrease, an increase, whether something has improved, then we have to think about, again, the order that we do our subtraction, sample A minus sample B, and how that relates to the language in the question. The one spot where we might have an issue is with our sample size. And with a t-score, remember, we always need to talk about our degrees of freedom, which is your sample size minus 1. Well, in these questions, unlike with matched pairs where each individual data point matched up to a specific individual or to a specific item, that's not the case here. So it really doesn't matter if our two samples are the same size or not. We may have in sample 1 that we have a sample of 200, and then in sample 2 we have a sample of 300. That's fine. So what we're going to do is to actually estimate what the degrees of freedom are. And we can get an estimate for the degrees of freedom by simply taking our smaller sample size minus 1. Now, because we're not directly correlating for each and every item, I don't know if my first item in sample A relates to the first item in sample B. You will not be able to know that with these. And because of that, your conclusions about cause and effect are not going to be quite as strong as they were with matched pairs. Let's go and take a look at what these questions actually look like and do some calculations with the use of Excel. Looking at an example for an independent sample question, here we have a toy company trying to decide between which brand of batteries it wants to include with a certain line of toys. So they're testing some batteries from a company called Everlife and some batteries from a company called Durabil. And then they want to decide whether there's a difference in the two battery companies. So there's a couple things that lead us to know that we're not dealing with a matched pair sample here. First of all, there's no way the items can relate to each other in each sample. We have one company's battery in one sample and a different company's batteries in the other sample. And another big indicator that this is definitely not matched pairs is the fact that the samples are different size. Remember, with independent samples that's possible, with matched pairs that's not. So if you ever see different sample sizes, Everlife we have a sample of 45, Durabil we have a sample of 42, so there is no way this can be a matched pair question. So that being said, it is a question about independent samples, and therefore our hypotheses are no longer mu sub d, they're about sample 1 minus sample 2. So mu1 minus mu2. Our null hypothesis is always that there is no difference. Well, what would no difference mean? It means that as we do the subtraction from sample 1 and sample 2, that the difference between them would be 0. The symbol with our alternate hypotheses, so is this two-tailed, left-tailed, or right-tailed? Well, here it just wants to know whether there is a difference in the two products, not whether one is better than the other, which means that in this case, we are doing a two-tailed test. So our alternate hypothesis that mu1 minus mu2 is not equal to 0. Okay, so our hypothesis is now complete. What is our level of significance? Well, for this question, it's 4%. So in order to calculate our probability, we're going to need to calculate our t-score first, and reminding ourselves what our t-score formula is. Okay, so we need to get all the information we need from each sample. We need the average, we need the standard deviation, and we need the sample size. And just to keep things simple, I'm going to consider the first company I see as sample 1 and the second company I see as sample 2. So from now on, EverLife will be considered sample 1 and Durable sample 2. So for sample 1, we need X bar, we need S, and we need N. And we need the exact same things for sample 2, X bar 2, S2, and N2. So for EverLife, we had an average of 28.5 hours, a standard deviation of 5.3 hours, and a sample size of 45. And for Durable, we had an average of 30.2 hours, a standard deviation of 6.9, and a sample size of 42. So calculating the t-score, we need to make sure that we divide that entire thing on the top by the entire thing on the bottom. So first I'm going to start with some brackets. We have X bar 1 minus X bar 2. We said in our hypotheses that mu sub 1 minus mu sub 2 will equal to 0. So there's no point including that in our formula. So on the bottom, we want that entire thing square rooted. So starting with brackets, we have the standard deviation of the first data set squared divided by its sample size, plus the standard deviation of the second data set squared divided by its sample size. And then we want the square root of that entire thing. Always easiest to use as few brackets as possible. Within this bracket, Excel knows how to follow the order of operations, so it's going to do the squaring before the division, and again the squaring before the division, and it's going to take care of all of that before it does any of the addition. The only thing we need to do is to tell it to square root that entire thing. So close off your bracket to the exponent 0.5, and we should get that we have a t-score of negative 1.282. Well, now we can go and calculate our p-value. So again, calculating a probability with a t-score, we have the option to right away choose whether we're doing a left-tailed, right-tailed, or two-tailed test. And we have that this is a two-tailed test that we should be doing. So selecting t.dist.two-tailed. This formula only needs two inputs. One is the t-score itself. The second is the degrees of freedom. And again, we are going to estimate the degrees of freedom by our smaller sample size minus 1. So if we hit OK, we see that we've got an error. There's something wrong with the number that we included. Now, what the problem is here is that whenever we do a left-tailed test, your t-score should be negative. Whenever you do a right-tailed test, your t-score should be positive. When you do a two-tailed test, really it should work for either a negative or a positive t-score. But there is a slight downfall here in Excel that it will only accept a positive t-score for a two-tailed test. So if we bring that function back up again, we can have this function work for us as long as we set our first input, the t-score, to be a positive value. So simply putting a negative sign in front of my cell reference will change negative 1.282 to positive 1.282, and in which case I will be able to get a solution for this question. Now, if you have any doubts whether that works, well, if you have a negative t-score, it should have to do with a left-tailed test. So if I do this formula for a left-tailed test equals t.dist for a left-tailed, we pull up our function, first input, our t-score, Second input are degrees of freedom, smaller sample size -1. Third input, for the left-tailed test, you have to put in that you are looking for a cumulative value. Hit enter. Now remember, what it's done here, it's given me the error only on one side. So because this is a two-tailed test, I would need to multiply that probability by 2, and we get the exact same answer that we did from our two-tailed t-distribution. So whichever way you do it, you should come to the same conclusion. And that conclusion is that based on the fact that we have a p-value greater than alpha, we do not have enough evidence to conclude that there is a difference in battery life between the two companies. Okay, looking at one more example where instead of given all the information, we simply have a set of raw data. Here we have somebody who's looking to open a new donut store in one of two possible areas, and she wants to pick the one that has the higher amount of foot traffic. So what we're supposed to determine from our study is whether location 2 actually does have more traffic. Now again, from what we see here, there's really no way to determine whether this is an independent sample question or whether this is a matched pair question. But if we go and look at the data that we're given, we see that it says we have a random sample of daily foot traffic at location 1 and a random sample of foot traffic at location 2. Now, if we look, both data sets are the same size, so that really on its own doesn't give away anything. But the fact that it's told us that it was a random sample at each location, what we would have to know if this was a matched pair question is that each of the observations applied to, say, the same day. So if these both applied to February 25th, and these both applied to March 3rd, and then these two to March 13th, if we knew that each one along the way applied to the same day, well then yes, we could go and use matched pairs. But because we just have a random sample at one location and a random sample at a second location, there really is no way of knowing if those values sync up. So we're going to have to do independent samples here. If we're doing independent samples, then we are using mu1 minus mu2 for our hypotheses. The null hypothesis, there is no difference. So sample 1 minus sample 2 should give us a difference of 0, in which case 0 will appear in our alternate hypotheses as well. Now, it's asked us to determine whether there's a higher amount of foot traffic at location 2. So here, we're definitely not doing a two-tailed test. We would just be trying to determine whether there's a difference in foot traffic. So for ease sake, let's call location 1 sample 1 and location 2 sample 2. And we need to think about, in general, when I'm doing sample 1 minus sample 2, what would indicate having a higher amount of traffic at location 2? Well, if there's a higher amount at location 2, we would have a smaller number for location 1 and a bigger number for location 2. So when I do location 1 minus location 2, small number minus a big number, we should be getting a negative value out of that subtraction. So if I do location 1 minus location 2, and there is higher traffic at location 2, mu1 minus mu2 should be less than 0. Our level of significance is 4%. And again, reminding ourselves of our formula for independent samples. We're going to need to find the average standard deviation and sample size of both location 1 and location 2. So for location 1, looking at the average, we have an average daily foot traffic of 2,709.4. A standard deviation, and again making sure we use the standard deviation for a sample, stdev.s. A sample size, and because this counts only cells with numbers, I can highlight just the entire column again. Similarly, we need the average standard deviation and sample size of location 2. Okay, it's good to remember here that when I see this symbol, there's no error that's involved. That simply means that the number I have displayed in that cell is too big to be displayed properly. So either it's just defaulting to show too many decimal places, or the number itself is too big. So if I simply, for display purposes, decrease the number of decimal places that I show, we are able to see what the actual number is. Again, the standard deviation. And finally, the sample size, which should be the exact same sample size as we had for dataset 1 or location 1. So now that we have all of the information that we're required to have, we can go and calculate the t-score. So we have the average of sample 1 minus the average of sample 2 divided by everything in brackets because we want the square root of the whole thing. So standard deviation 1 squared divided by its sample size plus the standard deviation of sample size 2 divided by its sample size. All of that to the square root. And we should get a t-score of minus 3.1338. So now again, we are doing a left-tailed test. So using the original version of tdist, t.dist, we get our first input is our t-score. Our second input are degrees of freedom. Both sample sizes are the same. Cumulative, yes. Hit enter. So based on the fact that our p-value is less than the level of significance, we have enough evidence to conclude that there is a higher amount of traffic at location 2. Now I would like to go over how we would handle two-sample hypothesis test when we would be using a normal distribution or a z-score. So starting from the very beginning, looking at the question and deciding whether this is matched pairs or this is independent samples, if we remind ourselves there's a couple dead giveaways that we are dealing with independent samples. One of those ideas is that we have a random sample in our first sample and also our second sample is random. If both samples are random, then there's no possible way we have any sort of way to link the first item from the first sample and the first item from the second sample and so on. So if we have two completely random samples, we have to have independent samples. The other giveaway that we're dealing with independent samples is when we have different size data sets. Matched pairs must be the exact same size samples. So here we have a first sample that has 25 items and a second sample that has 23 items. As soon as we see different size samples, we have to use independent samples. Now that we know that we're dealing with independent samples, we have two formulas to choose from. So we have to decide, are we using a t-score or are we using a z-score? Now, very much like last unit, the decision all comes down to looking at what differs in these two formulas. If I look, everything in these two formulas is exactly the same other than the reference to the standard deviation. A t-score, we can use the sample standard deviation, and a z-score, we have to use the population standard deviation. So it all comes down to, are we provided with the population standard deviations? We'll always be able to find the sample standard deviations. We're working with samples. You can always calculate the standard deviation out of the sample. But you cannot always find the population standard deviation. That information needs to be provided to you. So if we look here, when it talks about the sample, it does give us a mean of the sample and a standard deviation. So we have sample mean, x bar, sample standard deviation, s. Same thing with sample 2. We have a sample mean x bar of 38.6 and a sample standard deviation of 10.6. But at the end of the question, it has also provided us with the population standard deviations. It doesn't come down to whether we have the sample standard deviation or not. It's all about whether we're provided with this information, the population standard deviations. And here, because we are provided with the population standard deviations, we will be using a z-score. And now that we know we're using a z-score, When we get into Excel to calculate the probability, to find the probability dealing with a z-score will always be with the use of norm.dist. And we remind ourselves that with norm.dist, we always have that little help aid that we can use and remind ourselves of that silly little Mickey Mouse rule. We remind ourselves that that Mickey Mouse rule states that the first item on top, and now in this case it's that first bracket on top, that first bracket on top will be input 1 in norm.dist. The second item on top, and now it's the second bracket, will be input 2, and everything on the bottom has to go in as input 3. So in order to use norm.dist, we will have to find all this information. Our x bar 1, x bar 2, sigma 1, sigma 2, n1, n2, and all the rest of it. But first, let's deal with creating our hypotheses. When stating the two hypotheses, there's a whole bunch of information we can get in there without any care of what the question is. We can always get down the h0 colon h1 colon. We should always know that there's equals along with h0. And now that we're dealing with two samples, we remind ourselves that what we're trying to see is if there's really any general difference between these two samples. And we're always performing a mathematical operation of subtraction to find that. I can see that subtraction in my formula right here, mu1 minus mu2. Well, I think if there's absolutely no difference between these two different data sets, I should have generally the same numbers in my first data set and generally the same numbers in the second data set. So if I have the same numbers minus the same numbers, the result of that subtraction should always be 0. With two samples, there's even more information we can get into our hypotheses without knowing anything about the question. With two samples, the value that we're always going to be looking at is whether the difference between the first sample and the second sample is 0. Because as I do that subtraction, and having a result of 0 would indicate that there is no difference between sample 1 and sample 2. The remaining 3 blanks, these two and this one, will come down to information specific about the question now. So we've already decided that this is independent samples, and when it's independent samples, what we're making a decision about, remember that, about the population information, mu1 minus mu2, these symbols here are what should go into my hypotheses. So our null hypothesis is that there is no difference between these two things, where we get mu1 minus mu2 is equal to 0. The alternate hypothesis is again about mu1 and mu2. And now one thing we have a difficulty with dealing with two samples is it's not enough to just look at the word in the question. Right? If this was back in Unit 3 and we were dealing with a single sample, and we're talking about we want to know whether we've cut down time, so we're talking about a reduction, we would have used a mathematical symbol that implied reducing something, or a less than sign. But that's not enough anymore. We need to think about not only that word in the question, in this case cut down, but we need to think about that in combination with how we're going to do our order of subtraction. Now I'll always ask you to do either before minus after, or sample 1 minus sample 2. And if we think about the values we should see in these two samples, if we're talking about cutting down time, and sample 1 is before the application of these new procedures, we should have large numbers in sample 1, and then we've cut down time, so we should have smaller numbers in sample 2. So if we have a big number minus a small number, the result of that subtraction should be a value that's greater than 0. Large numbers in sample 1 minus small numbers in sample 2. Anytime we have a bigger number minus a small number, we always get a value greater than 0. And our mathematical symbol in our hypothesis should also reflect that. So with our hypothesis stated, just stating what our level of significance is, our cutoff point for when we actually do make our conclusion, we have a level of significance here of 5%. So just copying down the given information, we'll need x bar 1, sigma 1, n1, and similarly x bar 2, sigma 2 into n2. So for x bar 1, we had a mean in the before sample of 48.2 minutes. We were given the population standard deviation of 16.3 for the before information. The sample size we took was 25. Similarly for x bar 2, a sample mean of 38.6, a population standard deviation of 19.8, and a sample size of 23. So with all that information down, now using norm.dist, always norm.dist for z-scores, always reminding ourselves of that silly Mickey Mouse rule to help us out. So in this function, you see Mickey Mouse tells us this whole first thing has to go in as input 1. So we get x bar 1 minus x bar 2, input 2. So input 2 tells us it should be mu1 minus mu2. Well, remember, we don't have mu1 or mu2 stated over here anywhere. But remember, back to our hypotheses. In our hypotheses, we're working under the assumption that there is no difference between these two data sets, or we've already stated mu1 minus mu2 is 0, implying that there's no difference between them. So our second input in norm.dist with two samples will always be 0. The real work comes from this one on the bottom, where we've got to be careful with our application of brackets and exponents. Now remember, Excel knows order of operations. It will follow it properly, and always the fewer brackets you use, the better. So really, there is only one set of brackets we need here. One set of brackets for the entire thing that we're going to square root. It will understand when to apply the exponent, when to do the division, when to do the addition. So I'm simply going to start with a bracket. I've got my population standard deviation of sample 1 squared divided by the sample size of 1 plus population standard deviation 2 squared divided by its sample size. Close that bracket and take the square root of the whole thing. Cumulative will always be 1. Now there's only one thing we have left to do. Remember, this is a right-tailed test. And anytime we're using norm.dist, it's on us to apply the 1 minus whether we have to. It's on us to do the times 2 whether we have to. That's all taken care of with t-distributions for us, just by choosing the appropriate t-distribution formula. With t-dist, we can choose left-tailed, right-tailed, or two-tailed. With normal, it's on us to do. So anytime we have a left-tailed test, or a less than symbol here, we never have to do 1 minus. Anytime we have a right-tailed test, we always have to do 1 minus. Anytime it's a two-tailed test, it's on us to decide whether we need to do 1 minus or not. And with normal, that's as simple as looking at our first two variables. Is the sample variable higher than the population? Yes, the sample value is higher than the population value. 9.6 is above 0, which it always should be with a right-tailed test. So the only thing we have left to do here is to apply the 1 minus, and we get a probability of 0.0340 to 4 decimal places. Now remember, if this was a two-tailed test, we would have to multiply that value by 2 after we do the 1 minus. Well, finishing off the question, we simply need now to state our conclusion. And any time our p-value is less than the level of significance, we always have enough evidence to go with H1. Just moving this stuff out of the way for a minute so I can state those hypotheses. So as we said, because the p-value is less than alpha, we do have enough evidence to go with H1, which in this case means that we do have enough evidence to conclude that the new procedures have cut down on email time.